Testing, 1, 2, 3. Thank you. Okay, it's 4:02, and I'd like to get started because we've got a lot of material to cover. I realize a lot of people just got out of the operations talk, but please grab your tea and snacks and have a seat. Let's dive in. Okay, so welcome to this session. We've got a lot of interesting presentations, a lot of interesting material. I hope we can get some good discussion in at the end because I think this is an important discussion for the GENI community to dive into. The name of the session is Achieving the Programmable WAN. I'm going to be giving a very short introduction, and then we'll be going through a series of presentations that try to approach this question. Just as a few points of intro. The first thing I don't want to do is critique the title of this session. Do we mean programmable WAN? Do we mean programmable layer 2 WAN, layer 2 distributed LAN? There's a lot of sort of things that we might mean by this, but I hope that it's clear that what we mean is building a topology that is programmable. So let's sort of break that up into pieces. First thing, and this is mostly what we do in GENI, where the conversation stops, is we're trying to give the experimenters the impression of having your own private network. This is what the WAN part of this expression. So we're creating connectivity, possibly over a range of allocated resources. I say here, stitching is the primary example, though not the only example. The traffic is isolated. Your network can't touch other people's networks. It's isolated in that sense. It isn't necessarily performance isolated. And the traffic flows among the interfaces within your slice as configured. And whether it's going to be point-to-point, multicast, broadcast, depends both on you and how you generate the traffic and the underlying topology and its capabilities. And that's often where the conversation ends. That's, you asked for your topology, you got your topology, but in fact, it's really where GENI should just be starting the conversation. We should be starting there, and to complete the picture, we should be talking about how to control the traffic that is flowing within this network. What paths things are going over, what protocols, how we're changing the packets, if at all. That's really the programmable piece, and that's what I want to focus on here in this presentation. So just a little graphic. When we talk about just the WAN part, the topology that I've allocated, we've got some interfaces. What's behind those interfaces? Obviously, usually those are bare metal machines or virtual machines, but for the purposes of our conversation, those are interfaces, VNICs, NICs, MAC addresses that are connected through some set of forwarding elements, switches, what have you. But in order to make it a programmable topology, we need to have some of those things are not just switches, but they're programmable switches. And we have to have a controller, one controller for all of those, or different controllers. It doesn't really matter for our conversation. That's really what we're looking for, is ways to enable the topologies that we're getting, and there's a lot of tools out there for getting topologies, to make this kind of control possible. And that's really what I want to focus on here. Now, architecturally, GENI doesn't specify exactly how this is done, which is good. There's a lot of ways to do it, and I think that we'll be talking about a lot of different possible ways to do this. Switches or forwarding elements in general could be hardware or software. How we get from one switch to another is kind of, GENI doesn't specify whether what is invisible to us can go any way we want. The traffic can be stacked or tunneled or encapsulated. There are all kinds of different isolation mechanisms for keeping the network separated, whether we're talking subnets or VLANs. There are lots of legitimate ways to do that, so long as those basic requirements are taken care of. So, given that openness, that's sort of the subtext of this discussion, of this conversation. What are some of the options of good ways to give this capability to GENI experimenters? Now, we're not starting from scratch here. There are already a number of ways to do network programmability in GENI. There is what we're calling the GENI OpenFlow network. There's the Mesoscale, which provides shared VLANs connected to OpenFlow switches that a number of you have used for your experiments. And there's Foam and FlowVisor sliced OpenFlow switches, some sliced by VLAN, by subnet. So there are ways to do this. And you can also, as an experimenter, you can allocate your own OVS switches. You can put click routers in your topologies. These are things that exist in current experiments. So there are ways to do this. Each of these, and each of the things that we'll be talking about today, have their strengths and limitations with respect to ease of use for the experimenter and with respect to the power of programmability that it provides. So that's just an introduction. What I'd like to do in this session is invite 5 speakers to talk about their experiences and thoughts and about how we can step back and see what is possible and desirable in what we can offer, in what GENI can offer in terms of this programmable WAN capability to experimenters, in terms of what exists and what new directions we might go in. Nick Bastin is going to have a larger section. He's been doing a lot of work in something called VTS, the Virtual Topology Service. So he'll be talking, and then Eric Boyd will be giving a presentation on AL2S and the Flowspace Firewall. Then Rick McGeer is going to be talking about the GENI Experiment Environment, or G. Joe Mambretti is going to be talking about his recent experiences with SDX and Foam and Starlight. And Jerry Sobieski will be talking about his experiences in NSI and GEANT. So with that in mind, let's hand it over to Nick and start this set of conversations. And my hope is that we'll have a little time at the end for sort of an open discussion about the things that we've heard and what might be in common, what are some of the issues, and so on. So thanks. How about that?
I want this. I want the other thing. And I guess I want this thing. I don't really, but
Want to interrupt?
yeah. This is going to work poorly. Try it. No, not enough. Maybe that. Ha. Oh God. What have you done? Have to make sure I get the one from the right GEC. It's the exact same slide from the last time, I just changed the numbers. So I'm going to do a little bit of talking about the virtual, well, that was never going to work. All right. There was a demo last night of Virtual Topology Service. It wasn't particularly flashy, but it was sort of interesting for some people. I'm going to talk about sort of what we've accomplished since GEC19. Basics, what it does, what's been done, what's going to get done very shortly, and then what really needs to be done moving forward. One thing I will say is for people who don't know what VTS is, it's a label-isolated private network inside the GENI WAN. Label-isolated to mean that within your view of VTS, you have full access to every L2 label. The MACs are separated from other experimenters, IPs are separated from other experimenters, ether types, VLANs, access to all of this. At the moment, it's available at 5 InstaGenie racks, NYSERNet, Illinois MACs, GPO, and Utah DDC. We showed some of this working yesterday. DDC is pretty attractive because it has a lot of resources available, but at the moment, it's sort of limited. Current features, so we allow arbitrary intra-rack topologies, which is to say that if you wish to build a topology within a rack that has a bunch of VMs and then a bunch of programmable switches, you can very easily do that. And that works in a pretty straightforward way on the InstaGenie aggregates listed. There's not really any magic here. There's a little bit of tooling that helps you build your R specs. None of this works in FLAC or GENI Desktop or the portal or any of these things. So you have to write R specs by hand. You can currently connect your VTS slices to the Mesoscale OpenFlow core. So if you want to combine programmable OpenFlow data paths inside the rack with programmable hardware data paths on the WAN, you can do that. You can thank Josh Smith for suggesting that that would be a good idea. The current available data path in VTS is Open vSwitch. You can have it in either L2 Mac learning mode, which is to say that I want to build a topology, but I'm not interested in OpenFlow. I just need this interesting topology, right? I want to use different VLANs or something like that. Or you can use it in OpenFlow 1.0 mode. And Currently, S-Flow monitoring data is available, so you can make, in your RSpec, you can request that you get S-Flow data for your switches. So you can get the data directly from the device. And that's a very limited feature set, but that is what works like 5 minutes ago. And now I'm going to move on to what can work in a couple days. So probably what we'll announce after GEC, which should greatly expand this. So we're going to add more data path images. So if experimenters want to use Link or Indigo Virtual Switch or XDPD or theoretically something like Click, although Click will come a little bit later. If you want OpenFlow 1.3 bridges, we'll be able to offer 1.0, 1.1, and 1.3. I don't think there's any functioning 1.2 bridges. I don't think anyone really cares. We'll add NetFlow monitoring support. We'll add the ability to control your data paths over SNMP if the data path supports it. I'm not implementing SNMP for data paths that don't support it. And we'll have WAN circuits available, which means that if you just want to build, specifically the WAN circuits, particularly if you're not an OpenFlow experimenter, are interesting because if you want to get a data plane, a multi-rack data plane topology, we can give you one that just does MAC learning across the data plane, no stitching, nothing like that. No messing with any of that. We will offer operational actions for the ability to tap any circuit in your topology. This is super useful if you're doing OpenFlow things and you want to know what actually egressed your switch. It's a problem now. You make a flow mod, you think it does X, and it doesn't seem to be doing it, but you don't really know because you can't actually see the packet on the wire because that's a wire somewhere in Kansas and someone can't actually tap it. We have the ability to tap the wires between your data paths. So we can tell you what's really coming out of it. So for debugging, this is really nice. You'll be able to up and down any circuit in your network dynamically. So if you want to do Monte Carlo simulations or just test failures in your protocols and stuff like that, we can enable that. And you'll be able to dynamically reprovision circuit bandwidth, presuming it's actually available. Despite what that says about circuit bandwidth, and circuit bandwidth is available as a tunable parameter, these are not performance isolated slices. We share the same rack uplink as everybody else. So, if someone else is using a bunch of data and we don't know about it, I can't keep them away from you. So just to talk about scaling factors for a bit, this point of most InstaGenie sites only having 1 gigabit data plane WAN uplinks. At NORDUnet we have 10 gig, but at most places we only have 1. The core switches in the network that we use only support about 700 mapper entries, and that's if we're being really mean to every other experimenter, but just assuming for the moment that that is what we're doing, which leaves us with support for about 500,000 data plane max. It's a lot, but I mean that's basically a functional limitation right now. That's where we would top out. And then local connectivity within the rack is also limited because of the way we've implemented this. It's not a theoretical limitation, it's just one because of how we've implemented it by using raw PCs in the racks. So, I mean, this is pretty short. I just have a couple of next steps. We would like to support, as we talked about at GEC19, the ability for users to have arbitrary data path images. So if you want to write your own data path and you want to play with it in the Genie WAN, we want to enable that. And we would like to use the DCNAMs like ION and that sort of thing to get more circuits potentially across the WAN to sort of separate experiments from each other. That leads to more potential for performance isolation or at least backup paths and fault tolerance in the future. But again, we're still limited by rack upstream speed. We need more sites. Obviously, the 5 sites we have now are fun and interesting, but limitation on how many topologies you can build. We're working on exogeny support. Victor's somewhere. There he is. He's promised me glorious things. I surely hope he can deliver. But we'll get on that as soon as possible. And we have a resource utilization issue, which is that VTS is built on raw PCs at each site. And this is a little bit absurd. It's unfortunately a waste of that resource, but it's also the only way that we can do it right now. So that's a longer term problem. But that is the entire current status of the virtual topology service. Mostly, some of this assumes that people were at GEC19 or have heard about this or talked about it and so have sort of the background on these things. But I am certainly, what I mostly want to do here is lay out where we are and sort of get out of the way if people want to have a discussion about these various options rather than me sort of preaching to you what I think. So, do you want to take questions now, Marshall, or do you want to wait? I would rather possibly wait.
Well, I think I'd like to have questions about the general topic of how to do programmability within Genie, but if there are some specific questions to Nick in his presentation about VTS, now would be a good time too.
Denise? So, right, I can go back, probably. Whoops. Yeah. So the question is, what is this thing about untrusted code? So one of the things that would be really nice in Genie if you're a researcher is not only are you doing like SDN research a la using OpenFlow, but what if you had an idea for a better SDN protocol? Or what if you had a better idea for an extension to OpenFlow or something? We are instantiating these data paths on our own, on like this private VTS resource, and because of that, I trust all of the code I've put on it. I only let you have access to the things that I've vetted myself because I don't want experimenters killing each other, right? But we want to add functionality to allow the experimenter to essentially get a small container, which we will plumb their ports into, and then they can run their own process inside of. So you can run your own data path if you want to play around with your own data path. Does that sort of sufficiently answer the question? It's actually probably also how we will enable access to things like click routers, because while I have trusted click code, it's way too hard to configure without effectively giving the user SSH access to the thing, because it doesn't really support, you know, everything you want. And even if it supports SNMP and some things, that's a cumbersome thing for an experimenter to work with. Anyone else? Oh, so the question is, what do we mean about next steps, more sites? So you can only build VTS topologies between the 5 sites that were listed right now. And we need to enable more sites to give you richer topologies and more options. Insta-Genie sites are fairly easy to bring up. We have all the code in a standard image, but it sucks up a raw PC at each site. So that's kind of sucks. Rick. What I said was that would be a next step.
But the question is, why is that the current state?
Right, so to do what we do with packet forwarding and manipulation, I mean, basically our availability for a resource in an Insta-Genie rack is a VM or a raw PC. And VMs can't do what we want. A couple of things about that. One of the reasons is we actually nested virtualize. So we can't run VMs inside VMs in Insta-Genie racks. It's theoretically possible. We just can't do it with the way the software works now. And the hypervisor vSwitch gets in our way. So the hypervisor vSwitch that's provisioned by ProtoGenie would get in the way of the thing that I'm trying to do, which is lie to the underlying infrastructure about a lot of things that are going on. So the only way that we can currently implement this is with a raw PC, or some piece of hardware hanging off the switch directly, with nobody messing with the packets in between, because I want to mess with the packets.
I think what he's implying is instead of using one of the rack PCs, we could use a different PC like
right. I mean, it's
plug it directly in and not have it part of the rack, but have it just
right. I mean, there's an open conversation to be had of, you know, there are many options. Marshall's is the sort of path of least resistance at some level because it doesn't require anyone sort of rejiggering everything about how the rack infrastructure already works.
Unless, of course, you could rejig you could play with hypervisor switch.
Yeah, but that has implications for other experimenters, unfortunately.
So maybe I missed something. Why can't you use parallel resource in the rack?
We do, but they're scarce. I mean, that's why we don't want to. Well, and also, it's massively overkill. I mean, these are 16-core, 48-gig RAM, and I don't need anything like that. And then they only have 3 1-gig interfaces, and I need way more than that. So, like, they don't have the thing I want, and they have way more of the thing I don't want. And I'm wasting it, now an experimenter can't have it anymore. You know, so it's not great. On the other hand, you know, I hope that the utility of the service is such that people think it's at least, you know.
So we
Right.
And the flexibility of the vSwitch is limiting, right? So,
Yeah.
So it would be a useful action to come out of this if we could sit down and kind of identify some flavors of servers that would be useful.
Yeah. So NORDUnet actually has a piece of specialized hardware. It's the only rack where we're not using a raw PC. Although that piece of hardware is also massive overkill for what we're doing, but at least it's a completely separate piece of hardware that no one else had access to before. Other than we've stolen it from the NORDUnet traffic generator pool, so that's no good. But the PCs don't have to be particularly powerful. More cores are better. They don't need a ton of RAM, but the interfaces are the most important thing. And that's the other problem too. This is massively different at every site, right? One site might have, like for example, Illinois has 10 gig interfaces, so that's great. You want to build a PC that has 10 gig interfaces to do this for them, right? But most of the sites have 1 gig interfaces, so then you need to have a different thing that has 1 gig. You could get away with having 2 10 gig interfaces if you were in a 10 gig site, but at a 1 gig site, you really want a lot of 1 gig interfaces, stuff like that. So there's a variety. It's something that has to be talked about, and then like where does money come from to make that happen, and that sort of thing. Plus, if you want to upgrade a site to 10 gig, line cards cost a lot of money.
Do you have specific site requirements also, or are you just trying to do an experiment that could go anywhere?
It could certainly go anywhere. The site requirements that VTS have are no more restrictive than the site requirements of the existing rack sites. So like if there's a rack there, then you have data plane connectivity and someone who's paying attention, and theoretically things are plumbed there and that sort of thing. NLR notwithstanding.
How many interfaces would you like on a
It's not so much about, the question is how many interfaces would we like. It's not really about interfaces, it's about bandwidth. So if you look at an existing Instagenie rack, there's 3 data plane interfaces per PC, and there are 5 PCs in most racks, DDC notwithstanding. So that's 30 gigabits of total throughput. If you wanted to support max bandwidth of every PC using VTS as the only thing that, the theoretical max load, then you want some way to get 30 gigabits through the VTS node, which means you need 2 10 gig ports, because it's in and out duplex situation, right? If you don't care, and you're like, no, it's fine, 1 10 gig is fine, or 5, it's just a decision you have to make about what the provisioning is, and then just realize what you did. So on the 1 gig sites, you actually want a lot of interfaces, although you suck up switchboards, so that kind of sucks. At 10 gig sites, 1 or 2, probably. We also talked about, there are all sorts of things you could do. You could take data plane interfaces from the Instagenie raw PCs and plug them directly into the VTS box and sort of cut out the, say like, tell ProtoGenie that, oh, I want to use VTS, so bind all my stuff to this interface, for example. There are a lot of options that you could do, all better than others with different trade-offs. Denise?
What do you mean by this allocating discrete paths?
Oh, so in theory, across the core network, actually, there's a NYU NORDUnet Cornell would be a really good example, right? So they each have a 1 gigabit data path into the OpenFlow core, but that 1 gig data path meets I2 at a gig, right? So then I've throttled them back down again. But in theory, I could get a DCN circuit from, a stitch circuit through NORDUnet Ion to the other side, and then I'd have a gig from Cornell to wherever I wanted to go, and a separate gig from NYU to wherever I wanted to go. Because right now the OpenFlow core is, at any one link, it's a gigabit. And even if we get the whole topology and make loops, it's 2 gigabits, and only if I'm lucky and the paths are actually disparate. If we were to use stitching, we could provision more circuits. It won't increase the bandwidth available to any given rack because you're still limited by the upstream port on the switch. But where racks share a regional, they're also dividing out effectively a gigabit. And if you stitched, you might be able to get more. I need like a topology diagram to, words don't do this justice. It's not.
Discrete paths mean they're all going to the same place, but they're not end-to-end.
They use a different path across Ion or AL2S instead of, from each other. Or at least a path that AL2S guaranteed me had a guaranteed bandwidth reservation. I don't really care if it's different. But you could also imagine doing it for backup purposes, fault tolerance, that sort of thing.
So in your next steps, you're saying use this?
Yeah, so we have AMs already that can allocate these circuits.
You want to give this to the experimenter?
No, no, the VTS will do this underneath the covers. The experimenter is not exposed to any of this. Just like the experimenter is currently not exposed to the fact that VTS would use the mesoscale OpenFlow core to move their packets. They don't have to be an OpenFlow experimenter to get their packets moved across the OpenFlow core. We do that for them.
But it would be nice if the experimenter knows there are these kind of paths.
Yes, sure, we could tell you that. You could ask for them. You could also just use stitching yourself if you were really, I mean, you know. Well, no, but I mean, like, if you feel like stitching is complex, whatever I offer you that tells you about disparate paths is going to be complex. I mean, it's not necessarily going to make your life any easier.
You could use existing circuits rather than standing up your own, right? You could have two VTS nodes.
Oh, right. VTS would stand up infrastructure circuits and keep reusing them for different experiments. This is obviously an advantage of that, where you don't have to have every experimenter sucking up yet another VLAN. It's like, well, okay, you only asked for 25 megabits, so I'm going to throw 10 of you on this thing before I provision another one. Yeah. And then they live longer, they don't get torn down as much, I don't have to risk not being able to get them, all sorts of stuff like that. Yeah. Rob.
So right now, when you write an RSpec by hand for this thing,
Uh-huh.
right? I mean, I assume that it's going to be easier to teach tools like FLAC or JAX how to make these than it would to teach them how to because you're not talking about Flowspace or anything.
Right.
It's just which data path image you want.
Mm-hmm.
So am I right in being optimistic that this is a relatively simple thing to get into the tool?
I mean,
It's all our specs and aggregates.
And you have a library.
yes, also I have a library that generates these for you, so, but, I mean, this is, oh, bummer. All right, 150, maybe you can see that. That's an entire VTS request RSpec, which of course is mostly XML fluff, which asks for a data path, 2 ports, specifies a controller and a NetFlow collector. That's it. That's all there is to it. It's a manifest back. I mean, this is what we talked about last GEC, but there's a workflow where you ask for local circuits, it spits a manifest back to you, tells you what they are, and then you go ask ProtoGenie for your nodes to be connected to those circuits. So it returns this manifest, which is basically just a little bit decorated, and then you feed that back into a PG.
But it is a multi-step
Yeah.
process that
Yeah.
would not trivial beyond that.
Yeah. But it's not that, yeah, it's really not that complicated. It's much less complicated than dealing with Flowspace at some level.
And the plan is to have some automation to do those multiple steps for you behind the scenes.
Yes, actually, I was rushed in making these slides. One of the next steps would be have the tool that does this for you automatically, and a lot of that is done. But again, that's sort of more of a command line library type tool, and it would still be, another step to make that work in JAX or Genie Desktop or something like that.
But the way the stitcher does the multi-step part of getting a stitch circuit, doing that tool does the multi-step part of getting VTS.
Yeah, it's just, in this way, it's like stitching. There's a multi-phase part, but on the upside, there's no negotiation going on. So the VTS advertisement tells you if there are circuits available at this aggregate, and if there are not, don't make a request. You don't have to try it. Yeah, I would think so.
Okay. Thanks a lot, Nick.
Yep.
Next is Fred Ford.
You're going to tell me about where I can get more circuits from. HDMI or mini DisplayPort.
All right, hello. I'm Eric Boyd, for those who didn't make it to the plenary. I still work at Internet too, as far as I know. I'm not going to give the same talk again, but I kind of rushed through a lot of content this morning and wanted to take this opportunity to make it more free-form and interactive. I can talk a little bit. I got a bunch of questions after the plenary, and I can start talking to them, but I will feel free to interrupt with questions and stick your hands up whenever you want. So basically, I wanted to go into sort of another level of detail here in terms of what we're doing. So the software stack that we're basically running is the stuff that you see in blue. That's the Internet 2 software stack, and that we've done in partnership with Indiana University. So at the bottom level, those are the OpenFlow switches that we have there today. And currently, it's a mix of Brocade MLX-E16s and Juniper MX960s running in OpenFlow 1.0 mode. So that software is provided by the vendor. And I think for those of you who heard Luke's talk earlier this afternoon, made the acknowledgement that in some sense, it's a least common denominator thing. I mean, the plus is we're forcing multiple vendors to interoperate with each other, and we'd like to continue to do that and maybe even make it grow. On the minus side, if one of the vendors jumps faster than the other in terms of OpenFlow support or moving to 1.3, we're a little bit stuck. And so we're a little bit caught in that on the virtualization front right now. So from the perspective of the bottom up, right, the switch, Flowspace Firewall, which is basically our VLAN code, or our VLAN slicer code, you can think of as a one-to-many mux in both directions. So from the switch perspective, it thinks it's hearing directly from the controller. And from the controller perspective, it thinks it's talking directly to the set of switches. And so from both perspectives, it's an either-or direction. So Flowspace Firewall, I got the question, sort of, exactly what is it doing? And so specifically, it has two roles. It's a VLAN slicer, and it's a resource protector. And the second one will sort of grow in complexity over time. So the VLAN slicer aspect of it, what we're really trying to do is we're trying to create an environment where different applications each get their own VLAN range. So the idea is the OESS production instance will get a VLAN range of like 2,000 to 4,000. And the experimenter OpenFlow app over there on the right, which I showed the example of it being the ON Lab stuff as a for instance, would get VLAN range 100 to 200. So that's the key differentiator. Now that is not necessarily as flexible as people might want, right? I mean, it's one form of limitation, but it's a way to sort of split things apart. So one critique or one piece of feedback we might get would be, I want something broader, and we would have to start talking to understand what people would want there. But so currently what it does is it matches simply based on VLAN tag and port ID. And if it, for that particular port, if it's in your VLAN range, it lets it through sort of as a just takes it and hands it off. And if it doesn't, it drops it on the floor. Likewise, but there are other bad things a bad actor could do. So imagine instead of Onos up there, we had an application we called the Nutty Professor. We did this in a demo once before, which tries to grab as many resources as possible because it's a poorly written controller. So some of the key things that might be happening through Flowspace Firewall, as a for instance, is first of all, it might try to fill up the entire flow table. That would clearly be bad for the other slices. So one of the policy constraints that we need to put in there is just how many flow table entries that we can give to a particular slice. And these are things that we don't have answers to yet. We're starting to discuss, we'll come up with some fairly tight limits to begin with and then get comfortable. But if folks have comments either now or later about sort of, well, at a bare minimum I need this, that's the kind of feedback that we need. I'm not sure, honestly. I mean, that may be something where we negotiate it. I talked a little bit about the starting step was you tell us what you want to do. And it could be that what we need to do is set it based on, well, it's definitely got to be under this huge threshold, but we're going to make it as tight as we can and still meet your needs so that there's more for the next person. And so, so other bad things that we know an application up there could be doing would be to say, for instance, tell us So first of all, it might be how much of the flow table it consumes. Second, it might be how frequently it's pushing flow rules. One of the things we've noticed with all the different vendors is that the insertion rates in the flow table are fairly bad. They've each gotten better with every generation of the code, but they're not just limitless. So it's the type of constraint that we didn't necessarily have to think about in the past, but is a real one in this world. And so we probably have to have a resource budget on that. Third one Luke and I were talking about earlier today is packet ins and packet outs. It's not on the controller side. One of the questions I got offline was, so our controller may be very quick at accepting them, and that's wonderful, but the problem is on the switch side. Certain vendors just can't handle very many in their switch, so we have a limited budget of packet ins and packet outs as well. So these are some of going to be the real world constraints, which is why we need to sort of start with a dialogue about what it is you want to do. The goal here is, previously you probably ran your experiment in an entirely simulated environment and it seemed to work great, and you want to confirm that and validate it on the national framework, in a production environment. The problem is we have to probably limit you in some way, so hope you will have to be sort of customizing it to make it work. Go ahead.
So what's your thought about when a controller breaks those rules? Or do you just throw traffic on the floor and let them keep going, or at some point do you overclock the controller?
I think we'll probably have to have both kinds of behaviors. Very, very clearly, your experimental controller will be lower priority than the production infrastructure. So if it's a choice between shutting you down or impacting the production infrastructure, we will shut you down. That doesn't mean we won't let you run a new experiment with a tweak, but that'll be the kind of safeguard that we'll need to impose. Whether we can simply come back and say, effort failed, or simply have to quietly drop it on the floor, or just shut you down and start the experiment over, I think is one of the things that we're going to learn. And I don't think we really know the answer to that yet. But my intuition is that we would probably have to do a mix of things depending on what the extent of the behavior was. And just so folks are clear, I had it in here later. Let's see if I can find it. Yeah, so you're asking some of the questions from a policy perspective. This is probably worth talking through a little bit more in depth, right? So let's imagine you said, I've written my controller last night and I want it, I've tested it on my, my virtualized network, be it the one we just heard about, or whatever your environment may be, and I think it works. And we'd say, great, we'd love to work with you. First of all, what are you generally trying to prove? Just so we understand the context of the discussion. Second, what are the series of open flow commands you're going to exercise? What is the pattern that we're going to see requests? How much do you expect to use of various resources? We should have a dialogue about this. And the reason to have that initially is not because we're suspicious of you. It's because we're suspicious of the firewall, and we have to understand how well we're doing protecting ourselves. So this is not an attempt to throttle innovation in any respects. It's just because we have to build up confidence in the community over time that we're protecting ourselves. And so we'd kind of like to have an understanding of what the pattern of behavior in terms of your interaction with the switches that are being sent through Flowspace Firewall will be, and we'll get comfortable with that and have a dialogue. Then we have two basically test beds we can run this on. One test bed is the NDDI one, which is 10 gigs and a bunch of NEC switches, not dissimilar to Genie Mesoscale, but it runs the same software stack and it is on a national scale. And so running it there gives us an idea of what it'll be like on the national scale before we really do it for real, but is the wrong type of switch. So if there's a problem introduced by the switch type, we might not catch that there. The other one is the iDream infrastructure funded by Genie. And that one is precisely identical to the AL2S network, only smaller. So we've got 2 Brocades and 2 Junipers to emulate a cluster of 30 of them on the national network. And so it should catch most problems, we hope, that might have to do with that specific environment, but would lack the national scale and the total number of nodes. So if we work with you through both of those, and it seems to be forming well with both of them, then the next step would be to say, let's build a slice and do this together on the national scale infrastructure. So I recognize that that sounds incredibly cautious, but most of the people in here wear two hats. One of them is their, yes, we got to be pushing the envelope hat, and the other is, oh my God, don't break Facebook, or at least my boss's email, right? And so we're trying to balance between the two of them. Sure, go ahead.
So one of the primary things is you say there's is the VLAN range, that I can mess with the VLAN tag as long as it's in the set of VLANs that are allocated to me.
Yes.
What about the port numbers?
Also the port, well, so basically the VLAN range is on a per port basis. Yes.
I can mess with them, even if the ports are not consistent with the MAC addresses. I mean, I can do.
Yeah. Yeah.
Those are fields that I can.
Those are the two fields we have so far. If there is a missing field and folks are like, this is lame, I need more, and this is what I want, we'd be happy to entertain that conversation. But this is where we started out with what we thought we could do.
You go back to the slide, the diagram. So in this diagram, we have the Flowspace firewall, the central entity, which is what we've been doing in GENIC with the Flowspace firewall so far. But I'm curious, both in terms of the services that you guys might offer later, as well as potential experiments that GENIC might want to run. Anything that's going to be reactive, say like a layer 2 largest switch, something with a backbone, it's going to have this huge latency penalty if we have a centralized controller for the entire WAN. So do you have any ideas or plans on how to mitigate that control plane latency when reactive with this model of having a
Yeah, I think it's a good question, and I don't know that we've totally thought it out. I mean, there have been some discussions about whether we could decentralize Flowspace firewall. So part of this conversation is also going to be, so where do you run your experiment? Okay, so to run the particular one here that ON Lab did, right, took like an ungodly number of VMs and cores and everything else, and we had to scramble to put them all together to figure it out. If what you're doing is working from a variety of GENIC racks, as a for instance, it may be that we need to figure out a decentralized solution for a certain class of experiments, and that might be the type of change that we need to make as we work this way. So initially we're intending this to be centralized, which will have the penalty that you bring up, but it is possible we can figure out ways to mitigate that as we go forward.
You said that you're running two paths to support experimental networks and don't break email.
Yeah.
Well, doesn't this argue that these that this should be run on at least a physically separate channel, right? Wouldn't you just put the experimental services on a different color?
That costs us a lot of money in a different way. I don't know, John Paul, if you want to comment what that would take. I couldn't hear the end part.
Yes, very expensive.
Yes. So,
Yeah, but you get rid of a lot of machinery, right? If you did that, you wouldn't have to use Oscars or OESS, for example.
so we're using OESS for a particular thing, right, which is we want to run our production service. I mean, that has to be there anyway. That is part of our production service, is OESS.
The point is that you wouldn't have, the experimental labs wouldn't have to go through all that if it was running on a separate color.
Yes. Yeah, but I think the cost is really, I don't have the number off the top of my head, and I'll try to follow up and tell you what that would be. But I think it would be far more expensive than the rest of the infrastructure.
Well, yeah, but you have a much more effective infrastructure because you wouldn't be worried about breaking email. I mean, you'd be able to let experimenters do things that you're at least thinking about preventing them from doing, and you save yourself a lot of stress.
Yeah, but what we'd like to do is figure out, see, part of the reason for not doing that, as a counter argument, would be we would like to also be able to run additional services ourselves. So, I've presented it because this is GENIC as how do we give the experimenters their own slice to do something. But as a for instance, we would like to be able to run an alternate service. So you can imagine in one slice we run OESS, and in a second slice we run OESS, and we can stage between the two and swap back and forth. Or you could imagine that we might want to see if we can build a production grade layer 3 network without any routers in it, and offer that as a very limited SLA service that people can start experimenting with. And so this isn't just about creating one way for the production infrastructure and one way for research. It's about, can we support N researchers and M different services at the same time. But I think it's a really good point. Go ahead. Yeah.
Do you expect any of these steps to be automated from the experimental model? For example, if I use IWG, then I don't need approval or anything, and go get my results from my experiment.
So obviously that's where we would like to get to, right? Because making you go through these steps is obviously a hassle and could have a deterring effect on your research, and we would like to not do that. Whether we can do that, I think, is an open question, because we're also using the infrastructure, say, to anytime we change any part, like the iDream infrastructure. Whenever we change any part of that software stack, be it the vendor code or the OESS code or the Flowspace firewall code, we have to retest the whole stack to see that we didn't catch some interaction. And so we use it for lots of other things as well. And so we would be scheduling you in amongst those other tests. So like, this week, Juniper's asked us to upgrade the code that we're running on the Junipers from a pre-production version to a production version. So that took several days of testing. So we have to schedule kind of that against supporting the researchers doing this as well. So yes, I would like to do that. I think it'll be a little while. One of the things we're kind of asking for in the first N number of months is we're building up our own confidence in Flowspace Firewall. The faster we can get that confidence, the more barriers we will lower, and try not to make it such a high hurdle for you to use to start with. But we want to get to the point where this is not a barrier to innovation, which I think is the same question you were getting at, Rick. Is that some of the things that we're saying are going to sound like barriers to you being able to innovate. And so we are very cognizant of that, and we want to lower those barriers as quickly and as safely as we can. One more question? Okay, I guess we're good. Feel free to grab me afterwards. We really would welcome your feedback. I think I've gotten a couple good points here already. As you sit down and think about this and you say, would I really use this? How would this frustrate my process? If my grad students are trying to write a paper, could they really do it with this kind of infrastructure? If you see barriers to your actual use, please let us know. Likewise, if you want to be the first, one of the first guinea pigs, please let us know as well. We'd love to work with you, and we will make mistakes, I promise, but we'll try to fix them, and we'll try to lower the barriers to innovation. Okay, thank you.
Next is Rick McGeer.
Thank you. Thanks. All right. So, please. All right, thanks. So this talk is about the GENI experiment engine, which really should be better known by its subtitle, which is we're going to run Hello World across GENI in 5 minutes, in fact, in 2.5. Starting with the word go, the slide, all of our various collaborators. Glad to have them, thanks very much. So what's the goal of the GENI experiment engine? Well, the goal is simply to be able to run, the mantra is, simple programs to write ought to be simple programs to run and deploy. Or, if your programming environment, IDE, infrastructure, whatever, doesn't let me compile, run, and execute, compile and run, load and run Hello World in less than 5 minutes, it sucks and I won't use it. So, therefore, we set ourselves that goal. We want to allocate a slice across the G, which we're calling a slicelet because it doesn't come with quite all the machinery of a GENI slice. Upload and deploy a program, which we're going to do, in fact, in one click. execute it, then tear it down and get it all done in less than 5 minutes. And we wanted to have, Brian Lyles came by the demo of this last night and said, there's a greater value in what you're doing than simply making Genie really easy to use, which is you're giving people a sandboxed environment which is closed enough that the damage that a user can do is limited, which is helpful if you're running a production network, but it's not but it's powerful enough still that you can imagine doing some very useful things. One thing that we had as a non-objective is we weren't going to be all things to all people. We were going to try and do as much as we could, make it as simple as we could, but after all, what we were doing is customizing and simplifying Genie for simple experiments. So therefore, if you said, well, you know, gee, I can't do X, Y, Z on this, okay, you've got full Genie. Because if you're doing something complicated, well, you know, that's kind of what that complex and powerful and flexible infrastructure is for. But one other thing we did say is, well, we'll let you be able to use this as a starter for a full Genie slice. So you want to do something, you want to see how it works, get used to Genie, program it, play with it a little bit, see what an RSpec looks like. We'll hand you that eventually. Don't do it right now. You can do this, and then you can eventually move on and do more interesting things. So here's the architecture briefly, and it consists of a bunch of services. We will provide, the first thing that we're bringing up is the compute engine, which will let you allocate slivers across Genie and run into them easily. A storage service, which will look like a Genie-wide file system. You'll be able to store stuff into it, get stuff out of it, and it'll persist. And you won't have to use the compute engine in order to use that. Just say, open up this file, dump stuff in, pull it out as if it were a single Unix machine. And a messaging bus, again, which you can use as a coordination across Genie without using the rest of the stuff. So that gives us 3 services, and there were 2 design principles that motivated us. The first design principle is we weren't going to develop any new Genie facilities. What we were going to do is expose and simplify facilities that already existed. This was something that my colleague Glenn Reichart, the chief technologist at US Ignite, kept reminding me of, especially when we got into the network design. Gee, what are we going to do? Are we going to do? No, don't do that. Stop. You expose what's there. And if it's not there, well, somebody else in Genie is going to have to build it, but you aren't paid to do that. And that makes a good point, because we needed to be able to have exactly the set of facilities that an experimenter on Genie would be able to see, or a subset of them. And the second thing is, in order to be able to deliver stuff quickly, we pre-allocated wherever we could. So we grabbed stuff, allocated it, configured it, did all that stuff, and then when you said, hey, I want it, all we had to do was hand you a ticket. So those were the 2 principles, and then we have these 3 services, which I've already talked to. The compute engine, which sort of looks like a platform as a service kind of offering, in the sense that you can just say, here's a program, run it, right? Show you a little bit of that. The storage engine, which, as I said, is a global file system across the Genie infrastructure, and the messaging service, which is probably going to be RabbitMQ as a service. We're still designing that. So the compute engine is just really is a G-slicelet. This is just basically a network of Planet Lab slivers, again pre-allocated and with some software pre-installed. There's a private network between the slivers, which has the full port space that you can both serve stuff on and go stuff out. There's a Python VM installed and running, so you can upload and run Python programs without having to do any install. Pardon me. We pre-allocated it, which meant that we populated it with the credentials that you already need. We put in a burner key to use this with, and we deliver you that key. You'll see that when we hand you the slicelet. But notice that we made some decisions for you. In particular, you get a fixed topology. You can have any slicelet as long as it comes with exactly the same topology, right? Has the IP addresses that we, not you, get to pick. Has the VLAN tag that we, not you, pick, and has any color just so long as it's black, right? Those are the rules. We also will eventually we're actually making it easy for your stuff, and eventually we'll probably offer Fabric as a service. The network is actually something that we spent the most time on. Right now, you get 2 interfaces per sliver. Private network has full access. Public network, because of port contention, right? We have a single IP address to share between all the the G slivers on a node, is currently outbound only. We're working on a solution to that, which we may or may not get to. It's not part of our statement of work, but we're going to try and get it done anyway. The problem that we had is how do we expose the private network? IP addresses are specific to the pre-allocated slicelet. So what that means is that when you write your code, you don't know what IP addresses are in your slice, right? So what we're going to do is we'll tell you, okay, the names of your nodes are Utah, DC, Utah, Wisconsin, and BBN, which are the ones right now. And there will be symbolic and we will provide you a file of symbolic contents with those names which match to IP addresses. You can go ahead and use those in your program for local testing. There will be a file downloaded. You can copy and paste it into your code if you want. And that's what that resolution in a simple file means. Okay, the implementation. We're looking at 3 alternatives: tunneling using GRE, which Rob, I think, and Andy Bevere suggested. Use of VLANs. We have enough now, and there are more coming. One of the things that we're concerned about a little bit is performance of broadcast broadcast isolation within a VLAN. And whether or not this turns out to be a real concern, we're going to find out as we go through an experience on this. One of the things that we'd really like to explore, and this goes back to we will expose existing facilities when they're baked, is NIC's BTS, which you talked about a little bit earlier. We find that really, really attractive when we understand it well enough and NIC has made it a little bit more mature. We're going to look at that and see how we can expose it. The file system, once again, I said it looks like a file system over the GENI substrate. We'll have standard file system calls with volumes to indicate file location. The implementation that we're planning on, that we've started on, is Swift Repositories as a block store, and we're going to use Jude Nilsson's Syndicate as the metadata repository, which is currently up and running. The messaging system, we are still designing that. It's going to simply be global message queues. In other words, send to my slice, to my sliver, this message, pull it off, so you can coordinate. These things tend to be useful to coordinate distributed systems. The current design that we're looking at is RabbitMQ as a service. RabbitMQ is the messaging system that comes with OpenStack. We have with multiple clients, and it's got a nice RESTful API, which makes it valuable and worthwhile. We still don't know how many of these things we're going to run. Are we going to run it centralized, or are we going to distribute it across the slicelet ourselves? And we plan on having an initial implementation by GEC20 for people to bang on, and then I expect we'll change it as people say, oh, that sucks. Oh no, that's a nice idea. So we're still playing with that one. More to come in. Well, how do you use it? Well, you can use the G compute engine today, almost. As in, I can use it, you can't use it. There's a magic list of people who get to use this stuff. But it's in beta, and if you want to get on the magic list, come and see me or Andy, and we'll let you play with it. As what we're doing is we're handing out Planet Lab slices. So A, we need to allocate more if we get a rush, and B, well, it's still, it's still just up and running. And what you're going to do is going to log into the slice. Actually, rather than do this, that's stupid. Let me show you what you do to use it, assuming this thing ever comes back. So let's see if I can, here we are, good. All right, so this is me using GSlice, and keep your eye on this, because this we're going to time. So the first thing I'm going to do is start the timer, so you can prove that I'm really doing this in the kind of time I'm talking to. Then go up to the website. I'm highlighting the URL, which is stupid because it's going to change, and go in and say log in. We're using a Google account by now. By the time we make this thing real, it's going to be a GENI credential. It's just that when I was throwing this website together, Google had a nice callback. I've already logged in, so it just said, yeah, go ahead and share my email address with the app. And now I come to a page with 2 buttons: get a slicelet or free a slicelet, right? I can only have one at a time. That's part of the beta restrictions. So I say, okay, give me a slicelet. Click on that. And now it says, all right, here it is. Of course, this is instantaneous because we've got it. All we had to do is generate this tar file, which contains 4 little files that we'll see. So I'll click on that. We're 33 seconds in, and it could be going faster, but I was voiceovering. You can't hear the sound, but I'm voiceovering this, so I'm explaining what I'm doing as this thing is going. Oh, come on, Rick, click already. It's been 10 seconds. Here we are. So there I am, go to click. And now I'm going to download, so now I've got this tar file, which I'm going to open up. And then a decent practice here would be to copy it into some directory other than downloads, but I didn't do that. So here we are. Instead, I'm just going to downloads directory. And the tar file is ig8.tar. That's the name of the slicelet, ig8. I'm getting Instagenie slice 8. And the files are all in ig8. And in a second or so, I'm going to cd into that. And you'll notice that there are 4 files in ig8. A README file, which gives you instructions on how you can use all this stuff. A fab file, and I'll explain that in a sec. An ig8.pm, and the ig8.pm is the key file. That's the thing that's really important, because that's what's going to let you access the slice. And network.py, that's the file of symbolic constants that I mentioned to you earlier. That's just a little file that you can incorporate into a Python program. Or you can roll your own if you want to use something else. So now what I'm going to do is I'm going to change the mode on the ig8.pem file, make sure it's 600 because that's what an SSH key is supposed to have. And then I'm going to do something I really don't need to do, but which is to just copy it to my .ssh directory so that it's in a place where I keep my keys. And now I'm going to take a look at fabfile.py. Fabric is a Python, is essentially a way to execute SSH commands remotely in parallel. So in this case, I can run a command from my desktop. We didn't write that. We're just using it, and we're downloading this for you as a convenience. Notice that this is actually a Planet Lab, this is just a collection of Planet Lab containers, right? So you can log in using these credentials, username IG8, and key file name and identity SSH ig8.pem. And do this, or you can simply type in the commands that you're going to run on a node, your experiment, right here, which I'm doing now. So in run experiment, I'm saying, okay, go ahead and run this curl command on the nodes, and just go and talk to my web server, gproject.org. That's what I'm using just for the demo. And now I can go ahead and run the experiment. Now I've preloaded the map of the world onto my browser, and as I run the experiment, the various nodes are going to call back to the URL, say, hi, here I am, and at that point, the GENI experiment engine this web page displays dots on the map as it gets called. So now I've done all 4, and as you can see, the disconnecting says, well, the experiment has run, it's over, I've done the stuff you asked me to do. So now I'm just going to go back and free up the slicelet. It's done. I've run my experiment, it's all over, I've given back the resources, I can stop the stopwatch, and it's 2 minutes and 39 seconds. So. And a little bit of preparation. However, I did, by the way, also type hello world during that 2 minutes and 39 seconds. That was that curl command. Okay, so the G file system will be up. We hope to have running by GEC20. The GEC message system will have running by GEC20 for sure. You saw the compute engine is at demonstration level, so it's up and running. But the underlying infrastructure, which is Planet Lab, has been running for 10 years. So we'll be able to push this to production level pretty quickly. I mean, what we basically have to do is fix that website that a very incompetent programmer wrote in a few days. So we really do want that fixed. The G network, we've got it up and running to some extent. We're looking at design alternatives, as I talked about earlier. Stephen Treasure, who's my student in Victoria, has written a file system engine syndicate adapter, and we'll certainly be able to demonstrate at GEC20. Same thing for the message system. That's just waiting on me to get around to writing the code. So, as usual, the weakest member of the team is the guy who's designing the message system. And everybody else on the team, however, is rock solid. So we're in good shape, and we want to thank, in particular, all our collaborators and friends, particularly Rob, Jude, who's contributing as a freebie, and Rob and Nick, who have been very helpful on the network design. And Nikki, and Nikki, who allocates, who has helped us immeasurably, and she's taken off. But anyhow, Nikki has helped us immeasurably throughout all this, and Mark. And with that, I'll say thanks very much. Yeah. I'm sorry? No. I'll have to have a look at it. Thanks. Oh, you are here. Well, I said thank you if you for all your help, Nikki. Any other? Thanks. Thanks. Joe?
No Joe?
So Jerry, you're after Joe. Go ahead and I'll go and chase down Joe.
So this is a little bit of a stream of consciousness, but that's my daughter. I'm not a stalker. This is a little bit of stream of consciousness, but what I wanted to present was some thoughts and maybe a context of one way we might pursue this notion of programming wide area services. The first thing I'll just say is NSI. I think this is, you'll see later on in some of the slides why I put this just right out in the bat, right up there. I think we finally have an opportunity in our grasp to have a global provisioning system for circuits, for connection-oriented services. This is something we've been looking at for 25 years. And it's not perfect, but it's a really good approach to it. It's different than we've done it ever before. It's not about hardware, it's about services. And that's going to be the key, I'm sure of it. So look at this, and I'll make a few points about it, but if you want more information about NSI, there's a number of us around here that can elaborate in great detail. So some of the key things, there's a standard now, the network service interface, it's a standard. So we should be able to see either network domains starting their own network service agents, right? They're operating according to NSI. And your applications can integrate it. You know, one of the nice things of NSI is it doesn't require you be another network talking to it. You can be a user, right? It doesn't care. It explicitly deals with inter-domain provisioning. It doesn't care about what happens inside the network. It says, I'm assuming there's somebody that's going to, or some other agent that's going to take care of the internal provisioning of these service instances, right? The service semantic it provides is fundamentally just a connection, a transparent pipe from A to Z. There's a number of aspects that you can tune that, but fundamentally that's all it is, right? It doesn't mess with the pipe. It just says, where do you want it to go? I'll move data from where it comes in, and I'll put it out over there. It should be the same data. It should be the same latency, the same flow patterns. It's not always, but that's our goal. And it's also now being deployed within our network. So this is a service that's not going to be just something you use in your experimental environments. This is something that you can leverage that's actually out there as production. And that can be very useful. It doesn't get in the way of your experiments. NSI is a protocol that just provisions this stuff, and then you have a pipe that you can use for whatever you had intended. The transport links, these are just transparent pipes. There's no research value essentially to the pipe. You're just moving data, right? You move it to where you want to do the research. If there is a research experimenting or forwarding requirement, then you can break the pipe. You put something in there, either it's a virtual node or a virtual switch or something. You decide, oh, I've got to do some thinking at that location. You break the previous pipe and you just connect 2 pipes to a new one, right? Or 5 pipes or whatever, right? But the point is that the pipes don't do the interesting stuff. It's the switching nodes and forwarding nodes. And this provides this virtualization. It says that we don't really care anymore about what's underlying the pipe, right? Because at that point, all you're asking for is to move the information. So we don't care if it's a virtual service. It could be fiber, it could be down right at the hardware, or more likely, and it's going to be more so, it's going to be some virtualized service that's built up on multiple layers. You're not going to have access to it. Get that through your head. You're not going to be able to see everything down to the bottom. It's just not going to be there. That's actually going to be a security problem, and we just need to be able to address it, work in that environment. So when we talk about programming the WAN, what do we mean? Well, Marshall said, don't dissect my title. Well, I'm going to do a slide dissecting. Why do we differentiate the WAN from the MAN or the LAN, right? What's the difference? Isn't it just all networks? So making sure we understand what that difference is really important. I think some of the key telling points is that the WAN is multi-domain. Unlike what we used to do or what we had in our, well, I'll get to it in a second. It's multi-domain. You're going to have a lot of providers that providing infrastructure. They're going to virtualize that into some sort of service to you, whether it's a SONET circuit or a VLAN or a VPLS service. It's going to be core infrastructure. It's not going to be stuff that you fan out in your lab or your campus, right? It's going to be stuff that's where they're aggregating a lot of traffic, and it's not always going to be yours or experimental. So there's going to be these other production concerns associated with it. Programming the WAN is going to be done in the routers and the switches and the nodes. It's not going to be done in the pipes, right? And that's why I think there's a yin and a yang here with NSI and the SDN concept. This also implies that there are some other devices that are not network, right? You have routers and pipes and stuff, and there's an assumption that they go someplace where we dump the data, right? And I'm going to assert that a better way of thinking of this is everything's part of the network, right? What Sun used to say that the network is the computer, right? So even our hosts, even our end systems, we have to treat those as if they're part of the network. They might be a source or they might be a sink. Nevertheless, we're really only concerned about how they connect the network and who owns them, right? Because that's the 2 terms you're going to see me use a lot, visibility and authority. It's a multi-domain process. Otherwise, it would be called intra-domain. Let's see. What do we mean by domains? We had this discussion in the glyph last year. What do we mean by domain? And inside of 5 minutes, we came up with 3 different definitions. You could have a technology domain where everything was Ethernet or everything is SONET or SDH. You could have a service boundary, right? I give a Metro Ethernet service, right? Or you could have an administrative boundary. Now, here's somebody who sets the policy, authorization rules, and how you're going to actually be able to use, some infrastructure, right? And I think it's that administrative boundary that's going to be the litmus test for our programmable WAN. A multi-domain provision implies you have visibility to some map of the multi-domain environment, i.e. topology. And I think topology is still an open issue. There's been a lot of work done on it over the last few years, but I think a lot of that work is it doesn't quite cover all the aspects that we really need as we go towards these experimental networks. And so we should keep working on it. Let's not treat it as if it's solved or even that we're really coming around the corner on it. So I'm pushing really the notion of virtualization. I think that's, in this case, probably very synonymous with SDN. Networks aren't flat. The services overlaid on other services and over other services and still other services. They're not homogeneous. We got all kinds of different layers we're dealing with and all kinds of different technologies. And they're not public. This is what I was kind of adamant about a while ago, is that this notion that we can see everything in a global network is impractical at best. And it's a security risk to any provider who's ever dealt with this stuff. And given the revelations of the last year, you can probably say that issue about security and privacy and trust is going to be one of the drivers in how we build our networks, how we develop the technology we use in our networks over the coming years. I think the equation has changed dramatically by what's been revealed. Not that we probably shouldn't have already known it, but it is what it is. Let's see. We need a transport provisioning system that has global reach, because most of the work we have to do in the WAN is going to be just setting up the network resources we need between two locations where we actually want to do some thinking about that information. Right, and that's going to be that NSI aspect. Pathfinding, topology, I'm going to dwell on that topology issue because that's the missing link. A service that provides computational elements, that could be OpenStack, it could be GENI, any of the GENI frameworks, but something that provides all those thinking nodes in the middle. And they have to be virtualized because no one's going to give you control of their actual infrastructure. I'd like to be in the boardroom of AT&T when the CEO says, "Oh yeah, I let these guys change my network all the time." No, he's letting you change part of it, or he made a big mistake. So the virtualization process is what protects the CEO and keeps him in his job. We have to virtualize all these things so that we can give these resources to the users, the guys that want to program it, without letting them just run wild. That would be chaos, right? And plus virtualization allows us to be much more efficient with our resources. So here we come up with the two keys, right? Visibility and authority. We may have had that in the data center or our campus where we could see everything that was in our network. We knew what all the different technology layers are. We knew where all the switches were. And we also have authority to change those, right? So we have control and visibility of everything. But that's not going to be the case in a WAN. And so we need to find a way of essentially creating that same environment that spans these global distances. Issues about some topology topics. When somebody tells you what their network looks like, don't believe them. It's all BS. They're going to tell you what they want you to think the network looks like. The odds of it actually reflecting what's physically down there are very small. But it's all you have, right? It's all you're going to know, right? So you can't assume that you're going to actually find out what a service provider actually has engineered in the WAN in order to provide the services that he offers you. Even if he's offering you OpenFlow or SDN capabilities to program that infrastructure, odds are if you actually got a chance to look inside his network, what he's actually doing is much more complex and much more detailed. That he's abstracting it to give you a very summarized view of it. He might even be telling you stuff that's not even true. You can do that with topology, right? You can announce things that are just complete BS. You want them to be valid, right? If you want to do pathfinding on it, they have to be valid. But that doesn't mean that they have to actually reflect physically what's on the ground. And so once you kind of realize that, oh yeah, so really all I can do is I can take what they tell me. I have to trust that it's valid, but I wouldn't believe it. Again, it could be a security issue. It's certainly proprietary. Vendors are not, or carriers don't want to expose all those details. People start hacking on these big red flags that come hack at me. And it could be proprietary information they don't want their competitors to find out, right? So we just have to face that. Virtualized elements, right? Those are PCs. These can be VMs, anything. The transport services, we have services like Oscars, Audubon, glambda, OpenNSA. These are all NSI agents. They all conform. You can plug all those machines, all that software together, and they'll interoperate with each other, even though they might all be doing something different internally. So NSI, I think, is the key there. I'm going to zip through some of the rest of this. So what does GEANT provide? SA3, the service activity 3, it's a production service of GEANT, is the bandwidth on demand. It doesn't really provide bandwidth. It provides service guarantees, right? It provides capacity guarantees and scheduling ability, so you know you're going to have that circuit with a certain amount of capacity when your workflow needs it in order to work on the next repository. Standards, blah, 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 reach, wave services. We can also provide, traditional, kind of statically provisioned, but fairly quickly, because it's all in the Infinera gear. They can get it set up in a matter of hours once it's all approved. And we have a lot of partners. It's not just the GEANT core, even though that's got 40 nodes around Europe. We have all the NRENs that are participants in their countries. So we can also help engineer all these circuits through into the. So the last part I'm going to talk about is the testbed service. Some of you saw that in the previous session, but this is the European analog to GENI. We might have had the advantage of coming to the game a few years after GENI started. So I think in that respect we might have sorted through a few things after the US actually kind of did the heavy lifting. Nevertheless, so here it is. A number of requirements for it: a stable underlying infrastructure, be able to carry out high-risk experiments, insulated so that these experiments don't clobber one another, effective work environment, broad range of innovation. So we're not fixated on one particular technology. The goal was to provide a service that could integrate any type of technology, with the proper thinking and provisioning of it. So we do have open flow in the network and this SDN capability, but we're also looking at how we would integrate photonic resources, spectrum, or wireless or mobile capabilities. So it's got to be agile, it's got to set up and tear it down quickly, scalable. We really want this to move up to thousands of nodes in a test bed. And we want it to duplicate real-world environments. We've got three basic flavors here. The test bed, that's the one that's really closest here. I'll deal with that mostly. We have a dark fiber test bed. It's kind of on the side because we had some fiber left over. And we have this open flow facility, the GEANT open flow facility, GOF. It's the prototype that they built in 2 years ago in GEANT 3, not GEANT 3 Plus. These are two different projects. And it consists of 5 nodes around Europe. It's all software. Open flow switching with VMs. And so that's up and running, but we're looking at that as we're just holding it there, letting people continue to use it until TAS launches. And then this testbed service launches, and then we'll do that. We'll migrate them over. So how does it all work? We look at these networks as graphs, and we turn them into resource graphs, which basically says we have network links. There are resources as well. Kind of the reason we did this is that it allows us to treat all these resources consistently, and we can do some validation on port mappings and whatnot. There's a lot of dependency mapping that goes into this as well. A quick run through of the user view of this whole thing. The user comes up with an idea. It's a researcher, presumably. He comes up with an idea that he wants to test his idea, a network. He goes to a web GUI. We also have a CLI, but either way, it's the same front end. And he defines has a domain-specific language that defines the test bed he wants to realize. There's a lot more goo in here, but basically that test bed description gets sent to the resource manager. This is the GEANT agent sitting in Copenhagen on a server that listens to all this stuff and just goes out and allocates the VMs and the virtual circuits and the virtual open flow fabrics that you need. And then returns that all back to the user. And the user has the opportunity to add or relieve these. Quick example of some of the DSL that we're doing. Not quite accurate. It's been some changes. We're using Groovy to implement this in version 1. So it allows us to do a lot of changes quickly. I'm going to skip this because I'm running short of time. But this basically just says how we're taking our infrastructure using various software intermediate software layers to virtualize it, and then delivering that to the user. The testbed service is going to be over those blue sites first. Copenhagen. Does this one have the circles? Yeah, this has the circles. Copenhagen, then Bratislava, then Amsterdam, and Ljubljana. These are being installed over the next 4 weeks. So come April, we should have those first 4 installed. Hopefully, by the time we have a testbed panel at Internet 2, I'll be able to actually do a demo across some of those. We can reach out from the testbed capabilities to these virtual world in Europe, going through the SA2, the TAS bridging service through the bandwidth on demand of GEANT, and that peers with Internet 2, ESNet, all the others, right? So we can get out, and you guys can get in, right? We're starting out when this launches. We're giving classes. The initial classes are going to be starting in 2 weeks. Users can just log in. There'll be an anonymous class of users. You just log in. You can build test beds. They'll be limited, but you can at least get the feel of what the process is like. The next level will be non-anonymous, but it'll give you a little bit more duration for your test beds. And then the third part is a more advanced, sophisticated user who may be wanting to build their own resource definitions with the methods that we use to control them as well. So those require a little bit more sophistication. As far as the NSI goes, here's an example of the automated goal. This is the network that we've done demos on this for 2 years now, that uses NSI to set up Ethernet frame circuits between all those locations. An example of the multi-domain test beds where you can create a slice or a test bed up there from resources that are provided by many different providers. And those, you can see here, the providers can be sub-providers also. And finally, the last couple of slides I'm going to show you is how I think this NSI SDN thing balances out in the WAN. These slides are from a panel we had, I think it was about a year ago in Chicago. It's talking about where we had these SDN islands or open flow islands and how we would use NSI to link them together into an integrated facility. And in this example, we have 2 transit networks that are NSI compatible. We don't know what's inside those networks, but we don't care because it's just transparent pipes across them. What we're interested in is having these 2 SDN domains on the ends linked together into a logical adjacency. And then here's a similar situation. We have NSI transit networks, but inside those transit networks, we look a little deeper and say, oh wow, some of these are actually using SDN or OpenFlow to provision the circuits. They may be able to do much more, but certainly the transparent pipe that the end guys need is still put across there. That, you might think of that, I think, Eric, you might correct me if I'm wrong, that's certainly one of the capabilities Internet 2 now has, right, with the open flow through the core, right? So there's, and then you have this example where you just have your slices that are spread out across multiple domains. The NSAs are just these network service agents that do the interdomain provisioning. So the controllers can talk to the agents who set up the circuits, and then the agents get out of the way, and the controllers own the resources. Last slide. Any questions?
So you said something that's really bugging.
Uh-oh.
So I want to ask you to elaborate a little bit. Maybe I just misunderstood. But so we're talking about finally coming to a place where we're going to have this potential global capability to create NSS circuits all the way across many, many domains. But one of the things that you said was information is not going to be public, and that's going to be becoming information will be.
I said not all of the information will be public.
Okay, so I guess my question is.
And you won't know which is public and which is, all you will know is what's public. You won't know what's being held close to the vest.
So are you talking about things that might be useful to, say, network operators who are helping debug these?
Well, so we have a problem here. One of the issues we've heard before is that, well, what we want is the operators to have this special visibility so they can see end to end what's happening in a circuit. I'm going to assert that that's bogus, that's a model that's never going to scale. You're never going to have enough visibility to see through all the networks in the world. You can't compel all the networks to let you in, right? You just can't do that, right? They might, but you can't compel them to, right? And if there's one network out there that doesn't, it breaks the model. So what we really have to do is have a way of saying, well, we're putting this circuit out across all these different segments. I'm asking somebody to put up that circuit, right? And that person came back to me and said, I've done it. That agent, that provider agent, is responsible for that now. It doesn't matter how he did it. As far as I'm concerned, if it fails, I'm not going to call Japan or Brazil and try and solve the problem. I'm going to call the provider who said he did it, right? I'm going to notify him, or he better already know it's broken, right, or not performing properly, right? So, and then if that provider sublet that circuit out to 3 other networks, then he ought to be able to figure out which one of those networks is failing and go talk to that guy and say, look, I'm not going to pay you until you fix this, until it's working according to the specified constraints. You confirmed it, you're committing to it. It's essentially a contract. And so by doing that, we have this bilateral delegation of responsibility end to end, right? And now my operator, he'll know it's wrong, right? But he doesn't have anything, he can't fix it. It's not his job to go fix a network on the other side of the world, right? It's not my job as a user to go figure out what's wrong with some network. It's those networks' job, and we need to hold their feet to the fire to go fix it, right? And particularly if they're not going to tell us what's in their network, right? It just makes sense. Did that properly? Well, so
Can you guys take this up? We're running.
Okay,
We're
yeah.
running late. I'd like to give Joe a chance to, if I hear what he has to say.
Any other quick questions, or if not? All right, Joe, it's up to you, man.
Thank you, Jerry. Thank you.
Beer 30. Yeah. The mic is always hot.
Since we only have a Macintosh connection here, and I have a real PC, I will not show the slides. I'll just talk through them, because otherwise I'd have to borrow Heidi's laptop, and I'm going to spare her that. So what I'm going to talk about is something called the Petascale Science Prototype Services Facility. and programmable WANs. How do programmable WANs relate to this facility, and what is this facility? Basically, this facility is a National Science Foundation funded project to develop services and techniques and architectures to support large-scale data-intensive science flows. And these flows look a little different than the flows on most of the networks because they're extremely large and of long durations. And in fact, they can be single flows that are 100 gig end-to-end. We've been achieving 98.7 gigabits end-to-end. That's end-to-end as in the host systems. Currently, networks are not designed, they're not architected for that kind of service. They don't have a capability of doing that. They're designed for supporting millions of tiny little flows, not these mega flows. And if those mega flows came along, of course, they would not only destruct by hitting all those little flows, but the little flows would destruct. So you need a different type of architecture and a different technique. And in fact, programmable WANs provide the solution to this issue. So what we're trying to do with this initiative is provide the programmable capabilities to do large-scale networking capacity for a broad set of science domains, everything from computational genomics to Large Hadron Colliders to radio telescopes. Secondly, network services and resource programming for the capacity. So you actually have two mega themes. One is providing the capacity, the other is the programmability. And then providing edge access to the capability. So again, you want the edge to be 100 gig, not aggregations of even tens. And then exchange facilities that can support those services. So we have some reference sciences that we're dealing with. A generic one is large-scale capacity flows and file transfers. One is computational genomics and analytics. The bio community has been slow to come to the big computing world, but they have come in spades recently because the sequencers that used to cost 200 million now cost 2,000, and they generate 1,000 times more data, and they want to send this data around. Open science data clouds, high performance data clouds. A project called Datascope, which was developed by Alex Soleil, computational astrophysics from Johns Hopkins. LHC research, 8K digital media streaming, and one of the movies we have is, honest to God, 8K. It's 8,000 pixels by 8,000 pixels. This could be formatted in a way that one stream is 73 gigabits per second end to end. Now, 4K was the currency for the last Olympics. For the Rio Olympics, 8K is going to be important, and they're planning to put that in production. Scientific visualization streaming, petascale computational science using big data to and from the instruments, and large-scale storage streaming. So those are the driver apps. To put this into production, we have, with another NSF grant, implemented something called StarWave, which is a 100 gig exchange at the Starlight facility. And we're using that for the capacity side. We have 1,400 gig channels coming into the Starlight facility. And we've been trying the techniques to actually use that capacity. So another piece of this is actually utilizing that. One of our projects is with the NASA's Goddard Space Flight Center in Greenbelt, Maryland. We've had a persistent test bed with their high-end computing network being used to develop capabilities for geophysical sciences, for weather prediction and climatology. It runs from Greenbelt, Maryland to our facility. We also extended, over the last 5 years, we've extended it to supercomputing conferences. On that, we have shown that it's possible to achieve 98.7 gigabits per second end-to-end, including, as I said, edge systems. In our last test bed for SE13, we used a 100 gig NIC produced by Acadia Optronics, as an edge system NIC. The disk-to-disk transfers, that's memory to memory, disk to disk. We hit a world record in our last demo. It was 93.7 gigabits per second, disk to disk, wide area network. Another project we've been working on is one called Remote I/O. This is a project with the Naval Research Lab, and what this does is it divides within that large capacity single stream. It has streamlets that are individually addressable, programmable, and changeable. So you can, on the fly, look at the data streaming at 100 gig and alter the data that's moving in that channel across multiple parallel streams. We showcased this at the last supercomputing along with the NASA stuff. And we also did large-scale transfers over large-scale transfers of large-scale data for the Open Science data grid. Another one we did was a joint project with the National Institutes of Health for Computational Genomics, 60 gigabits streaming. For all of those, the wide area that we used was the Energy Science Network because they have a highly programmable network infrastructure. For example, we needed 100 gig to come out of Washington, D.C. for a variety of these demonstrations, NASA, NIH, Goddard. And Brian Tierney's test bed does not go into Washington, D.C. There's only the production network. In general, you can't go to a production network and say, gee, you have 100 gig from Starlight into Washington. I want all of it, please, for a week. Can't do it. But what ESNet can do and did do is they said, tell you what, through programmable networking using OSCARs, we will give you two 50 gig channels. We'll take one that will go from Washington, D.C. into Starlight into Denver. We'll take another one. We'll go south through Atlanta into Denver. Now you have your 100 gig end-to-end because we're going to slice this up and do two paths. They did that very straightforwardly. It's a very nice principle, and this is the kind of network that we would like to see in the future, as opposed to, no, we can't do it, to let's use programmable networking and actually do it. And it was done successfully for 6 different sets of these 100 gig demos. Can't show you the images of these spectacular science visualizations. But I'll end by noting that you have the capacity, you now have the programmability emerging, you have the star wave type exchanges for the high capacity. The missing element, the one missing element is the software-defined networking exchange, which is a theme here, and that's another facility that we're building. I gave a talk on that earlier. What that looks like at Starlight is we built on our international OpenFlow testbed where we have sites in Asia, North America, South America, and Europe. And we have had a bit of an exchange doing interdomain signaling and resource discovery. More recently, what we've done is create what looks like a large-scale virtual switch built from a lot of sub-switches based on OpenFlow. So you have a virtual switch with addressable programmable elements within that switch that you can segment and partition, give to different communities, and allow them to peer. Our goal is to have an exchange capability for multi-domains where there's no knock in the middle. There's no central authority in the middle. Individual domains can talk to each other because we have 130 private networks in our facility. We don't want to get involved. We want these people to talk to each other and find resources. And finally, I'll just note what my friend Jerry Sobieski said. we've been working with the NSI community. NSI is actually a standard being developed by a standards organization. It's well documented. It was developed as an API for control frameworks at the different glyph exchange points, and it's a nice starting point for international large-scale WAN transfers. We've been using it effectively for years. The current project is to turn that into production. We're making it production at Starlight. There's a number of networks in Europe putting it in production. We would like to see it in production in the US. It's a very handy facility. How would that work with an SDX? It would be another tool that would allow access to those capabilities at the SDX. So a key element for an SDX is having resources advertise themselves, saying these resources are available at these times, and then having a signaling system that asks what resources are available where, tie them together. It's a dialogue. You need some ontologies for that. You need some semantics for that. Within this emerging world, there's some rich semantics emerging, such as the network definition language coming out of the University of Amsterdam, extended by Renzi through OWL, and others, some nice signaling capabilities. NSI is well documented. I suggest you look at that. And with that, I'll close. Thank you.
Any questions?
Questions?
I think you could have done the 58 ways on Internet too if we had 100 people board at Starlight at the time. So I think we could have done the same thing.
Well, by saying ESNet did it, I didn't mean to imply you guys couldn't do it. Okay, so yes. Yes, thank you. Yes, yes.
That's actually cue for what I was about to say. I want to thank all of our speakers, and thanks everyone for sitting through. I know we ran over, and I want to ask all the speakers to send me their slides so I can.
You have a flash drive?
The wiki for this session.
Russ wanted me to remind everybody that there's a panel that has a secret reception associated with it. So you want to go to that panel. It's okay to arrive late. It's across the street. Look in your agenda, and he's hoping everybody will be there. Thanks.
Good night, everyone. Thanks. That was great. Thank you, Joe.
You're quite welcome.